Okay, I'm going to try to record this. I'm not going to do a lot of editing. I just hopefully it will make a lot of sense to everyone. But I want to go over this equivalent steady state model for the induction motor, which will help us understand the vector control better. And so if we look at this model here, the main takeaway is that this is the standard T-circuit model that we've covered in class already. And the torque expression here is actually representing the torque delivered to the air gap. So that would be the torque associated with this term right here. The power delivered, associated with the power delivered here to the rotor. Resistance term divided by the slip. So the first step in isolating that voltage is to start with this generalized equivalence circuit, which is where we started before the rotor quantities were referred to the stator side. Now, we didn't cover this in class, but it is covered in the Christian textbook. And the key to this whole expression here is that we can have some liberty in how we do the referencing between rotor and stator sides of this circuit using this referral ratio A. So what that's saying here, and this is kind of a key point because it kind of points to the flexibilities you can achieve with different types of vector control and how that can be understood in terms of a steady state circuit. So if we go back and we looked at this conventional circuit right here, if we could somehow get rid of this term right here, we could control the voltage, ER, by controlling the amount of magnetizing current that we're putting down this branch. So we can introduce this arbitrary ratio of A. And if that ratio is set to Lm over Lr, we can make this happen. Now, in order to introduce this A factor, let's look at what we've got here with these, what we did. So we used to have up here J omega LS, that would have been the leakage term, and we had J omega LR, that was the rotor leakage. That's the thing that was giving us so much trouble. Just stick that in there, then you're going to get this. And then over here, A equals 1 would give you the same thing. You'd be just subtracting off the LM parts. I hope that makes sense, okay? So what we're doing, we're just changing what A is and get this into a different form that we can work with. So we won't be doing this, we won't set it equal to 1, and therefore we're just going to make it arbitrary to start with. And by setting it equal to Lm over Lr, it looks like this. It goes away here and it changes what this equivalent inductance ends up being on this side here. So you truly have a situation where the phasor current IS is controllable, and the real part of it is the torque producing component of it, and the imaginary part is associated really with the magnetization, the magnetizing flux in the main path here, the induction motor. So it's kind of like this is a flux term and this is a torque term. Similar to what we were doing when we looked at the synchronous motor, wanting to control a current for torque and a current for flux. So the induction motor, if it wasn't for that leakage inductance, gives you this natural type of a circuit. And so we use the controls to make it look like it has a different A factor, A equal Lm over Lr, and that will make it look like this. Okay, so we can now try to analyze this new equivalence circuit, and it will help to simplify it just a little bit. I also want to point out something that happened here. If we looked at this circuit here, we've actually got the rotor current going in this direction and stator current. They're both going into the branch. Now, normally we think of it going this way, and I think it's simply going to end up being a convention of the way things are looked at by, the way that Professor Gennady looked at this in his notes, I think. So it'll be clear in a moment. But to kind of simplify the math, let's come up with a kind of an L primed value here that's equal to this. So use this LS prime, and the effect of doing this turns ratio transformation, you can kind of see here, is all what you're doing is you're really just changing the current. So if the stator referred current, instead of it just being what we typically called in this conventional circuit here, the rotor current here, it's like the actual rotor current primed. Remember back in the early derivations, I'd call it IR of the rotor, and then when you refer it to the stator, it became IR, and that's what it is here. But now that is changed to this term. It's changed by the ratio here, and then it's going to show up here. It changes the voltage across this branch. So you have the what's going down the magnetizing branch here. There. And you've got that magnetizing current in there in this new circuit is completely responsible for the rotor flux and for ER, rather than the air gap flux in EM. So that's kind of the main point here. You know, the conventional, that branch was air gap flux, and the magnetizing voltage applied to that, EM, which was basically the stator voltage, and subtracting off the this voltage drop here, okay, across the two terms here. That was the way in the conventional system, and essentially you kind of go back to, say, constant volts per hertz, keeping this term right here constant. It's almost proportional to the voltage that you're applying to the stator. And if the frequency were to change, you would change the stator voltage and keep constant volts per hertz. That's the old way, but now with this change, it's going to say, well, let's instead use the magnetizing current to control the flux, the rotor flux. And the ER, which is proportional to the torque. So we've kind of created 2 degrees of capability, because we can then have these things aligning themselves in two directions along the imaginary axis in a phasor representation for the field flux, and then along the real axis for the torque. That's what we've got going on here. And then it's possible to have this expression right here. This is kind of the whole key thing right here. That torque expression. Torque, it's a function of a rotor flux that we control, and the stator component, the torque component of the stator current. And then we can control this rotor flux by controlling the imaginary component of the stator current. And it's really very, very similar to the DC motor, where you've got the lambda AF equal, you've got the lambda AF term right here. And you've got your armature current right there. There's your lambda AF there. And then you just have these, this is just a constant times that. So, in summary, you've got a torque component of current, and you've got a rotor flux component of current. And as I alluded to, we've got this new expression now here for the torque. And if we have also, we can come up with the expression for this voltage across. Really, I guess you'd say the air gap, right, to control the air gap power. So the voltage across RR over S. That you're going to control that by controlling this ER term, and that ER term that's proportional. ER term is proportional to this flux, and it's proportional to the electrical frequency. And then the flux is controlled by controlling the imaginary part of the current right here. So what you do with this circuit is you can then derive a slip frequency term here. So that's what this part of the lecture or the lecture notes are addressing, a slip frequency. And that is, if we look at this revised expression for the torque part of the current, it would tell us that the torque part of the current is proportional to the magnetizing branch current right here, and the slip frequency here. So we can control the torque part of the current by controlling the slip frequency. That whole thing is derived right here. Okay, so try to understand how they came up with it. Basically saying that this current here, that torque, trying to think what the best way to, how best to describe it. Going back to these equations here, you got this ER, write that in terms of the flux, all right, the lambda R in terms of the magnetizing branch current, and then look at that ER voltage as something that you want to try to eliminate from this expression here to get that expression. And so it's really kind of, I don't know how much more to beat this one to death, but in the comments he has here, I'll just read them, is that we modify the conventional equivalent circuit to achieve an orthogonal rotor magnetizing current and a torque producing current. We really did that by selecting this kind of artifact of a turns ratio between the rotor and the stator to refer the current differently to the stator side, and that's what enabled us to do that. And so if that's the first comment, now the second comment here is so that you could have used the conventional circuit in terms of air gap flux linkage to come up with this. That's a magnetizing expression here for current, and you could say that there's this torque producing current IR, but the problem is that these two things are not orthogonal, so you can't get the kind of decoupling that you need, especially under the transient conditions, to make this thing work. So you have to apply this steady state circuit. It really ultimately applies to the transient circuit as well that's used in the controls. Okay, so this is a little bit of a hard circuit to look at here, but it's looking at it in terms of the phasors. So let me see if I can flip. Yeah, that wasn't too hard. So we're really looking at the phasor analysis of the whole thing. And we start with the currents that we're trying to achieve, right? So we know that we can control, say, the speed and position by controlling this term right here, okay, the torque part of that current. And so your controller will control the speed and position by controlling the current that is attributed to torque. But we have to, and we also need to ensure that we are controlling the field as well through the imaginary part. So you've got the total current, let's say that you're supplying here, the stator current is made up of these two things. And then from there, you say, okay, well then what to get that current, you've got to control the applied stator voltage. So we can say I've got the reactive drop across the stator leakage inductance term, the XS prime term, and the resistive, and then that synthesizes the voltage that you need to get right here. We can also, instead of using these terms that we were talking about before, the IS torque, stator part torque, stator part of the flux, we can say, well, those are very similar to the DQ values in the transient model. So we've got this branch down here is controlled by controlling the D-axis current. And then this branch right here, we control that by controlling the Q-axis current. So the D is aligned with the rotor flux, and the Q-axis, the Q current is in quadrature with it. Another key point here is that when we looked at the steady state, we were using RMS quantities, but when we're looking at, so these are RMS quantities here. When we're looking at the dynamic model, these are peak quantities, so they're just different by the square root of 2. Controlling the peak values. Okay, so how would you implement this in a in actual hardware with controls? So this is a kind of not getting bogged down in how say adding space vector control and everything to it. What the point, this just to clarify here, what's happening is it says we have a current regulated PWM block here. We're receiving these stator current commands right there to ensure that. You know, that could simply be, one way to do it is, you know, you've got this you've got this torque command. Let's try to fill in a few gaps. This could be the output of, say, a PI regulator on the speed. So we've got some speed feedback coming back from somewhere. Now, we've talked about that a little bit, but this would have to be an observed, you know, it's estimated quantity, because where we need to get the omega r is from this position that we're measuring. The position that we're measuring right here, and so there'll have to be some kind of a speed observer to get that. And then we have this IDS command, which we could use that to let's say control think of it as if we have to field weaken or we want to operate at some nominal rotor flux value, this is a controllable quantity, it can be independently controlled, say. And so then you go into this with this slip calculation, and this is a key point right here, is that it depends upon estimated values. That's why this little hat there is there. So you've got an estimated rotor inductance and an estimated rotor resistance. One of the things, these are tough, but for example, the rotor resistance is sensitive to temperature. So one of the challenges with implementing this was the fact that you needed to have some kind of model reference adaptive controller or something. And this is an opportunity, I think, for, say, machine learning and things like that, too. It's, instead of using those old techniques, we've got better techniques. We've got data that we can use to improve our model, let's say, based on features that we can extract from what we measure. It's just a little bit of an aside. But that's a sensitivity that you have. Now you are controlling the frequency, but you need to know what the slip is. So well, I take that back. Now this, you're controlling this whole term, this slip frequency term right here. If you then were to integrate that, that gives you a slip position, and if you add that extra position to the feedback from your encoder, assuming that you've got all the scaling and everything else lined up, you get this that is the commanded. Now this is the same as the theta E. That is, we're going to do this, I believe, in the synchronous reference frame and do a transformation on the currents in the synchronous reference frame to achieve this kind of a controller. So there's this example here. I'm going to give you this little example to work yourselves. Go through this problem here. Find IDS, IQS, and the slip frequency to find the rated torque. And then you can find the steady state rotor flux linkage involved. So this is a way to just, we can do the steady state analysis on this whole thing. So what we just described is what we call an indirect scheme. And it's indirect because you measure the rotor position and then you utilize the slip relation to compute the angle. So when I kept referring to something called indirect field-oriented control, FOC, this is what I was referring to. I think this has always been the most popular way of doing field-oriented control for induction motors. But there are alternative direct approaches. So this is what you do there. You have these direct field-oriented control. To do that, you need to have surge coils, or let's say Hall sensors or something in the air gap. It requires a specially wound machine, but you can more directly measure the position and even the amplitude of the fields, and then directly control the flux to control the torque. That would be your direct field-oriented control. So you have these two ways of doing a vector control that gives you this 90-degree angle. So I'm going to pick up where right here into the next set of lecture notes here. And I'll post all this on Canvas. It really picks up with the indirect field-oriented control of an induction motor, rotor flux oriented. So basically it's called that because, you know, we're controlling the rotor flux lambda r in the way that we described in the with that steady state model. So you have a steady state and dynamic models that can be looked at, and then the dynamic responses. So we can go back to the DQ model for the induction motor that was derived. What we have is we've got the D-axis voltage. It's got the resistive drop. You have the this is kind of like the LDIDT term in a way here. And then you've got the coupling term from this Q-axis, cross-coupled term. That's kind of like your EMF term. And then if you look at the Q current, you got the same thing going on here. The Q-axis R, LDIDT, and then the coupling term, cross-coupling term right there. And you've got similar expressions for the rotor. The only difference is since you short-circuit the rotor, you're not putting a voltage into them. You're only putting these voltage here. And this is really, you know, coming this is coming from the output of your PWM controls, really. That's the switched voltages applied are going to drive controllable variables within this. You've also got different stator and rotor flux linkages here. So we had the stator flux linkage proportional to this D-axis current. I'm thinking this is more like torque related, so I'm going to use this blue. That's your torque Q-axis flux linkage. And you can also come up with a rotor winding flux linkage terms as well in the D and in the Q here. So if we looked at the electromagnetic torque expression here, one of the many expressions that we introduced when we derived this a couple lectures ago, the developed electromagnetic torque. It's a function of this dx Q-axis is right. You've got D-axis rotor flux and a Q-axis stator current. You've also got this term here subtracting off of it. It's reducing that. Now, I believe what you're going to want to do to get the max torque per ampere is you're probably going to want to drive that to 0. So let's go back and look at that. Now this is just simplifying terms here. Lm over the ratio of LR plus Lm, that's this LR term here. Now you can take these expressions here and come up with look at it as a matrix, do matrix inversion on it, and you can come up with currents in the D-axis and the Q for the rotor, these current terms here, and they end up simplifying down to this term and this term that's proportional to a d-axis current. This term is proportional to a q-axis current. So, these are all lined up with the q and the d. That's what you get when you get the dq currents from the fluxes. You're using the dq currents, dq fluxes. Unlike the voltage equations where you've got the cross coupling between them. So that cross coupling only shows up in the voltage equations. Now you got your stator flux leakage terms here, and the idea is to substitute in the rotor current expressions. So you got that rotor in the D, you got this in the Q. Math's probably pretty hairy, but then it's going to ultimately simplify down to these two expressions here. So remember, this was that LS prime expression that we just came up with. LS prime times IDS, and then we had the LM over LR times the d-axis, the LDR. And we have this q-axis current here. Now let's keep going. So this is explaining what I was just pointing out, simplifying this thing down here. And we got these revised dynamic expressions then that can be plugged into this. So essentially what you're doing is you're taking these lambda d and lambda q terms being equal to this. Those are the terms going back up to the voltage expressions here. Okay, so we've got let's go back down here. We've got lambda ds. This is a synchronous frame flux linkage in the d-axis, synchronous frame flux linkage in the q-axis. Go back up here, there's that term. You've got both of them right here, see? So the idea is to plug these other terms that were derived from all this math to kind of terms that are simply in terms of what's in this stator referred rotor flux linkage terms and the stator current dq current terms. So you plug those into this, and now you have, as it says here, a dynamic model with stator currents and rotor flux linkages as state variables that are controllable. So basically, it's we're talking about them like this: a lambda E prime dqr would be this equal to lambda v. So I think j lambda qr, I think that's right? That's what you mean by this. So you can treat this as a state variable, and I dq, the stator, would be IDS plus JIQS. Let's go back and let's kind of keep going with that at the moment. We can look in the steady state, things simplify down quite a bit. And I'll try to think what's canceling out in the steady state. So basically in the steady state, that means that these terms are zero here in the rotor side, and this is zero, right? Basically in the steady state, d dt is s. You set that to zero, right? And so now you've got these are your steady state equations right here. Now here's where we try to understand what we're doing with the field-oriented control, which we described previous with the steady state circuit. We got this steady state expression for the d-axis voltage here, and the q-axis voltage. And the idea is that you want to get the rotor flux linkage aligned so that it's all along the d-axis. So you don't want any q-axis rotor flux. So basically you're going to want to try to drive, I think, going back to this expression here. What you're doing is you want to force that equal to 0, and you want to force that equal to 0. But you want these guys to be there, okay? The d-axis terms. So what we did was we looked at the d-axis voltage. Check that here. We got this term right here. Just subtracting, it's subtracting off this simple kind of coupling from the q-axis circuit. And then if we look at the q-axis circuit, q-axis voltage, we got rid of, well, we didn't get rid of anything. It's the same thing, see? Now, but if we do this, the d-axis voltage is equal to the magnetizing inductance times IDS. And if we go back and look at this expression here, we have this term showing up. The difference between the electrical synchronous frequency and the rotor speed, or rotor frequency. Well, we know that is the slip frequency here. So we can, that's equal to that. And I think this, I can't explain this right now. I think if we go back, but basically what this tells us, how we got this, I think we have to go back and look at it, but it's really saying if you could control the ratio of the Q to D current with the slip controls that ratio, and then there's this thing you don't have a lot of control over, that's the transient time constant of the rotor circuit, right? But you do have control. If you have independent control of these, you can do quite a bit. And under the field-oriented control condition, it ends up simplifying the rotor voltage as well. Again, we're assuming that the derivative terms were set to 0, and we forced the Q-axis part of the rotor current to 0 with the indirect field-oriented control. So the rotor voltages are simplified. And this also tells us another thing, that the rotor slip frequency isolated out of this expression is going to be proportional to the ratio of the Q-axis rotor current to the D-axis rotor current times that rotor resistance. So from all of this, you can derive the relationship. The idea here is let's derive the relationships between the Q-axis stator and rotor currents. So we have this is the Q-axis rotor current relates to the Q-axis stator current by this ratio of inductances. They're very close, you know, just the leakage inductance difference. And since we know that, we can substitute the slip equation and where we had this we had this expression here. The key point here is that you can't measure this. Can't measure that. But if you write it this way, you can measure this. And you can control this by controlling the slip frequency. So kind of drilling down on that IDER and what you've got there. You've got this is the flux linkage expression for that. This depends on both the stator and rotor d-axis currents. Now we can't measure or control the rotor, but we can do it with the stator. But if we force this Q-axis to 0, the rotor current is only in the d-axis, and then we'll end up having, as a result, we'll only have a rotor d-axis current IDR will only exist during a dynamic change in the flux linkage of, so basically the derivative of lambda dr prime with time, it's going to, in the steady state it's 0, but during dynamics you have this thing right here. Okay, so that's affecting this current. It's the only thing that's really affecting it. Otherwise, in the steady state, this says then you would have to say that IDR E prime in the steady state has to be 0. So we've got these relationships for both transient and steady state behaviors that you can build upon now. And I think I'm going to have to stop at this point. I think we've got enough to work with to start on another homework problem. I'm going to be looking at that and start to talk about a lot of issues drilling down on the indirect field oriented control. And I think it's important to do this because indirect field oriented operation is the most common vector controlled, field oriented controlled drives. It was commercialized, I'd say, probably in the late 90s, but it became kind of your standard fare. But there was a lot of research on this when I was a student. And a lot of it had to do with, you know, some of these issues that are being brought up in the rest of this lecture. Just kind of looking ahead here. Dynamic response decoupling, adapting, recognizing the parameter dependencies that you have on this behavior, on the transient behavior, and trying to overcome any impacts of the changes in parameters on the steady state behaviors of what's going on. And so I want to we'll go over the rest of this in class, but that kind of gives us a good point here, and very good understanding of indirect field-oriented control of induction machines.